Yeah, it's 2:30, so I guess we'll get started. Hope everyone's enjoying the conference so far. I think there's like one more session after this one. I had a pretty good time. Hope you guys did too. Can everybody hear everything? It's good? All right, cool. So this talk is called ANSI Schmansi. The title itself is kind of tongue-in-cheek because it's while I'm going to use the word ANSI to refer to like the ANSI standard, what I really mean is by ANSI is anything which is supposed to be supported across multiple vendors. So normally when you're talking about ANSI, there's like a very specific thing of the standard itself, but we're going to go into a little more specific definition that I like to use. So a little about myself. My name is Serap Sarkuni. I'm the founder of JackDB. As far as my Postgres involvement goes, I work on I contribute a bit to the JDBC driver, and I also contribute to the Node.js driver. And I also hang out a bit on IRC, so if you ever ask a question there, there's a chance I might actually answer it too. So ANSI itself there's an ANSI standard for SQL, and there's actually a couple ANSI standards for SQL. So the two most recent ones are 2011 and 2016, and each standard successively builds upon the previous one to add a new functionality that's supposed to be incorporated in what would be considered an ANSI compliant database. So Postgres supports most of 2011, but it also has some other parts of newer standards inside of there. The standards themselves just keep evolving. So like there's a 2003, 2006, and some of the functionality that's in these standards, as it gets added over time, it's things which other databases might have already supported in some non-standardized fashion. And the idea of the standard is to have like one unified approach so that if you're using different systems, you'll have approximately the same functionality within them. So you have things like JSON was added very recently in 2016, even though Postgres has had support for JSON since, I think, 2012 maybe. So when people talk about writing applications which are targeting an ANSI platform, there's a couple of primary reasons they do so. So one of the big ones is licensing costs. If you're not sure about how much you're going to have to be able to spend on the actual platform you're deploying to, having an ANSI, having your application developed towards an ANSI platform like that lets you eventually change what the platform is. I'll switch from database A to database B, and hopefully everything will just continue to work. So kind of avoiding that lock-in from the beginning by only sticking with features that are commonly available is something that people do. The other thing is you don't necessarily know where you're going to be deploying either, because it could be you might want to change it down the road, but it could also be that your company doesn't know exactly what the production system is going to be. So in the interest of not having to have like a 23rd hour change of saying, oh, we can't use that feature because we're using this other type of database now, you kind of avoid those kinds of things. One of the big problems, or many of the big problems with that approach, is that if you kind of go to the lowest common denominator of what's supported in ANSI and what's actually supported among the different database vendors for ANSI SQL, you end up with this kind of not fun things, and it makes simple things very difficult. So one example is like when it comes to typing for data types, there is no standard typing for like a UUID. So what you end up doing is you have like a string field inside of your database, and instead of being 16 bytes for what a UUID actually is, of just 16 random bytes, you'll have like 36 bytes to actually encode the full string value of that UUID. When it comes to constraints, you're limited to like the bare minimum of what's supported across different systems for like basic checks across the row, or maybe like unique key constraints. And even like the SQL, like writing SQL itself, you end up being limited to the lowest common denominator of, okay, I'm going to do a select by ID on this one value. I'm going to do an update by ID on this one value. And you don't really get to use the full power of everything that you're doing. So some people will say, oh, but I'm using an ORM, and it's going to transform my, whatever I'm trying to do into the native for that language. It'll be more efficient. It doesn't really work that way, because while for like the simplistic case of just doing like individual key updates, your ORM will be able to handle it. When you start doing complicated things, you want to be writing the SQL, and then you're still tied down to, hey, if I'm going to support 5 different platforms, what's the one thing that's actually going to work across these? So the reverse of that is if you go kind of database specific and just say, hey, we know we're going to be using Postgres or Oracle or MySQL or whatever you're using. You can kind of leverage whatever's actually in that platform. So Postgres has tons of data types. Oracle has its own kind of functionality. MySQL has its own functionality. And whatever that is, like you can embrace it in your application. And one other nice aspect of this is if you know what you're actually going to be using, what you're using in production should be what you're using in development as well. Way back in the day when people were doing, like in the early 2000s, people were doing like Java development. They'd have like a in-memory database like H2 or something for running their unit tests, and then they'd go deploy afterwards to like Oracle or something else. And at the time, it seemed like a good idea because I can run my unit test really quickly or whatever it is, and I have to install multiple copies of Oracle and have to deal with licensing. But what ends up happening is that you end up writing stuff that's going to work on both platforms, and that really chews into what you can actually do because we can't really write a test for this, or we're not going to do this right now, and it's not going to work. So obviously, you guys are at a Postgres conference. You guys, I'm sure, all know that Postgres is the greatest open source database that there is. It has tons and tons of features, and as far as databases go, is one of the most standards compliant that there is. So while this talk itself is about going beyond that to things that aren't necessarily part of the standard, Postgres is really good at being standards compliant. And what's even more so, like one of the things I like about it is when it's not standards compliant, a lot of the time it's because the standard itself just doesn't make any sense. So there are things in Postgres where it deviates from the standard, but it does so because the standard itself, if you try to actually do what it's doing, it either wouldn't be useful or it would be something that would be so difficult to implement that there's no point in actually having it like that. So it's almost like common sense dictates what's actually part of Postgres. So this is one of those things that more and more over time as features get added, you really appreciate it. So when you're going beyond using ANSI SQL, again, the goal here is you want to expand upon what's actually possible inside of the system that you're using. And some of the stuff could just be like a different way of writing something. So it might be possible with ANSI SQL, but it's just going to be a little easier using something that's not ANSI. The next level of that is stuff which might be really difficult, but now it's really easy, like using some non-standard stuff. And then the last level, which is the fun one, is when you start doing stuff which just would not be possible otherwise, and all of a sudden you're like, hey, I can do these weird combination of things, and it just works. So the way I'm going to kind of flow through this talk now is, I'm going to start off with some simple stuff and just everyday SQL that you can use if you're kind of embracing Postgres as your data platform, and then we'll kind of move on to some more fun things afterwards. So the first one, anyone who's come from like the Oracle world, let's say, you're required to always supply a relation when you're doing a query for a select. Postgres, you don't have to do that. You can just say select and give a value, it'll come up. People who are familiar with the standard know there's actually another way of doing this where you can use the word values, which is part of the standard. The problem with that is it's not actually standardized across all the different vendors, so it still doesn't work. So although it exists in the standard, you can't actually use it. You still need to have some kind of table there. Whereas if you just know you're using Postgres, who cares? I can just say select test and I get my value back. I love data types. I love the concept of having a well-defined structure for your for all your database objects. And the flip side of that is when you're interacting with things, you want to make sure that the values you're interacting with, whether they're literals or whether they're parameters inside your code, they actually have the types matching what you're dealing with. So Postgres has this great syntax for casting where you just put : and then the type afterwards. And if you ask, again, this is like a personal opinion on it. It's just so much easier on the eyes. Instead of having that big cast over there, you just say, hey, this is a date. Regular expressions, if you're not familiar with them, are a way of defining pattern matching, but it's kind of like but on steroids. So Postgres supports regular expressions out of the box. You can use them in all kinds of places since it's just an operator just like anything else. So you could have a constraint defined with a regular expression. You can do like clauses with them. If you set up trigram indexes on your text field, you can actually have them have regular expression comparisons end up being indexed as well. If you're coming from a place which doesn't have these things and trying to recreate what a regular expression can do, it can be very frustrating. So even the simplest things of trying to say, hey, I want this username to start with a letter and have be alphanumeric or whatever, you can do those things using but you end up with these big blocks of it's got to be like this, but also like this and this length and this not. Whereas with regular expressions, you have this nice concise representation of it, which might even match up with the exact same one that you have inside of your app code. So you have this one definition of what you're doing, and Postgres supports this stuff out of the box. There's two kinds of coding in Postgres. One is with single quotes. The other one is this Postgres-specific type of coding called dollar coding, which is really useful if you have text which has a quote inside of it. So if you see these examples, the first one over here just uses regular single quotes, and you can escape a single quote inside of there with another single quote. So you could just use single quotes everywhere, which is the standard way of doing things. But if you have some text which you want to make a little more legible, instead of having to escape everything, you can just have it inside of dollar quotes. And if your dollar quotes itself, if the text has the dollar quote syntax inside of it, you can actually give a custom tag so that you can have a more specific dollar quoting that won't match up. So again, there's nothing really like you can't do an ANSI here. It's just a little easier on the eyes, which I like. Some other interesting things you can do with dollar quoting, and just like combination of like dollar quoting, regex splits, things like that, is you can just dump data into a query using the dollar quoting, because by using dollar quoting, I don't have to worry about the internals of what's in there actually matching up with a quote or something like that. It'll just be whatever the raw text inside of there. And then you can use this really cool function, regex split, which will use a regex to split that line into multiple lines, and then just do like data munging on top of whatever's coming in. So this isn't something you should do on like a regular basis inside of an application. But if you just have like, hey, I have this data, I want to dump it into a table somewhere, I want to get something going, it's really easy to do this stuff directly inside of the SQL that you're doing. So in this case, I have this text. This string gets broken down into 3 different lines with this regex split function. And then I'm splitting the lines again, this time by commas. So this is like a poor man's version of a CSV parser, which is not very standards compliant. And I'm splitting that into different fields, saying like, array value 1 is going to be the title and the start date, the end date. And I'm actually casting them to dates too. So the end result of this is I start off with this text blob, but I actually have a strongly typed set of data I can insert into somewhere. So one other like just table stakes as far as databases go is the transactional isolation levels. If you're trying to work with many different kinds of databases, you either have to make sure to configure them to be in the same structure, or you have to make very small guarantees on what you could actually do. So the default transactional isolation level in Postgres is read committed. So what that means is when I start reading something, if I'm a reader, I see whatever the state of the database was before my transaction started. And if someone else writes something in the meantime, it doesn't interfere. The writers only end up blocking each other. So if 2 people try to write at the same thing, they'll wait for each other. But as a reader, I never have to worry about having locks or anything like that. From an app dev perspective, this is usually what you want. You start off saying like, when I'm running a query for displaying some data in like a web app or something, I don't want it to wait. And I probably just want to see the state of whatever the thing was in the beginning. So having it be the default in Postgres is, as an application developer, is very pleasant. So kind of moving on to more fun things you can do inside of SQL. Generate series is one of many functions that come stock inside of Postgres. You'll probably see it most of the time when people are creating examples for either test cases or just generating data. The way the function works is you give it 2 parameters. The first one's like a start, and the second one's an end. So this generate series of 1 to 100 will generate the numbers from 1 to 100. So you can do this in like other systems which don't have this have a function for generating these things by saying, hey, select start from some gigantic table like all objects if you're coming into the Oracle world or whatnot. But what happens there is you have to make sure does this thing actually have enough rows to do what I want to do. So like if I know it's like less than 1,000, I could probably do it over there. But if I need like 10,000 rows or 100,000 rows, I might not necessarily have that in that information schema view. So then you start doing like weird stuff of like unioning them together to get around it. Whereas in Postgres, you can just say, hey, I want 100 rows. And this function is actually, it's not even just with integers. You can give it like a date and another date and say, like, give me the ranges between these 2 dates or timestamps. What you can also do in Postgres, rather than using the actual function to do the ranges between dates, you can just do the addition yourself too. So usually, this is the kind of thing I'll usually do, where I'll just have the range be, hey, I want 100 rows, and then start from today, and then give me all the days backwards from there. So 1 day back, 2 days back, 3 days back, 4 days back. So you can kind of transpose from just numbers into some other data type, transform forward. Another, I don't want to say Postgres specific feature because this actually is like a standard concept. It's just not implemented consistently across different platforms, is lateral. So lateral is a way of being able to reference a relation that's in the same the same part of the query in the from block, but in your join clause itself. So in this example, I have customers, and I'm lateraling to this purchases to say, hey, give me the most recent purchase for each customer. So if you're doing this for like a single column, you can do it without lateral by just saying, hey, I'm going to do a scalar subquery inside the select clause. So where this transaction date is, I could say select transaction date from purchase where it's this particular person. But the reason lateral is like a step up above that is you'll see I'm able to pull back as many columns as I want. Because instead of just getting back that one scalar value, I can pull back a whole row. And you can do a lot of more interesting things with this as well by combining multiple things together in the lateral. If you're coming from a world where you don't have lateral and then you go toward lateral, like this is one of those things on like a regular basis you get really happy because like, oh, I can just do lateral here, pull back 10 fields or whatever, and like decide afterwards. It's really useful. So another one where that falls in the category of yes, this is part of the standard, but no, you're not allowed to actually use it because nobody, like literally nobody else supports this besides Postgres, is filtered aggregates. So filtered aggregates, if you're familiar with, aggregates are saying like sum, count, average, and whatnot. So the traditional way of doing a filtered aggregate where I only want some subset of the data in there is to put a case block inside of the aggregate itself. So that you say, hey, case when the type is Postgres, give me a 1, otherwise give me a 0, and I'll do a sum. But what I'm really trying to do here, what I'm really expressing is, hey, give me the count where the type is Postgres. And the distinction between this and doing it in the where clause is if I have one larger set of data and I want to compartmentalize it into saying like type A, type B, type C, by doing it with one pass, I'm able to create them all at the same time. The equivalent of this in Postgres with using filtered aggregates is you just say filter where type is Postgres, filter where type is not Postgres. On the one side, it's, you're directly expressing what you actually want to do. You're not like going out of the way to say this is a sum times whatever. And it's less code to read too. So for someone going through this, hey, I can tell immediately what this is. I'm not summing to get a count or any weird thing like that. And this has been supported in Postgres for, I think since like 9.3 or 9.4, I forget. It's been there for a while. Yeah.
Which is more efficient?
Which is more efficient? So the question was, which is more efficient? They're actually the same. Like the second one, the filtered aggregate itself is. Let me see.
No, actually, it's more. I was going to ask exactly the same question because I'm wondering how it's implemented inside, and it actually looks like. Is it like not doing it twice?
I'd have to find someone who's actually worked on the aggregate code. It's definitely not doing it twice because it's getting the rows and applying that filter to the. I think the way this is implemented, the aggregate function only gets called when the where clause itself is the predicate matches.
Okay, so then it's identical. Then
yeah.
Like effectively identical.
Effectively identical, but I think technically it would still be faster because you're not doing extraneous operations for a case when sum versus just a count. In theory, a count would be marginally faster than a sum.
I think it should be implemented internally, like basically the same way.
Yeah.
Okay.
But again, a lot of this stuff for me, it's not even like a matter of efficiency. It's just like being able to see what you're doing and understanding what the code is. That itself is already worth so much because it's like developer time versus things just running time for microseconds. Any other questions on filtered aggregates? All right, so kind of moving on to data modeling. So databases, you're structuring data. Probably the biggest part of that is what is your data going to look like? What are the shapes of things? Postgres is really good at this. It has like so many data types. And coming from a world where you don't have these types is like, it's almost like a sad existence where you can't even define like a Boolean in another system. Like you're just saying, oh, I'm going to use an integer for this. 1 is true, 0 is false, or whatnot. Postgres has tons of types. You can actually add your own types. Like you can define custom types. There's extensions for additional types. They're always adding new types. So I'm going to go through a couple that I like. The first one is Boolean. I use tons and tons of Boolean fields inside of like everything that I build. There's more often than not, you'll have some kind of concept of like, is this true? Is this false? Is it yes? Is it no? Is the customer active? Is it, just the general concept of something being yes or no. And while you can represent it using like just a, like a 1-byte integer for like a 1, 0, or there's like a bit type in some systems, technically it's the same amount of storage space because in Postgres, like a Boolean is implemented as a 1 byte. But from just understanding what the query is doing, writing SQL, reading SQL, it's just more pleasant having a Boolean type. Because if you look at the SQL over here, I'm saying where is active is 1 versus just where is active. Like you're expressing what you're trying to do more clearly. And then when you start having more complicated situations of actually trying to assign a value to something, you see it a little more clearly. So in this case, I'm saying, hey, I want to assign is active where bar is equal to x, y, z. So rather than just directly doing that, I have to take the result, put it into a case, and actually pop out the 1 or 0 from there. Whereas in the Postgres specific one with a Boolean type, I can just say, hey, set is active equal to bar equal to XYZ. Like you're directly saying what you want to do. Anyone reading this will know what that is, and there's no no hopping back and forth between these extra values. So the text type in Postgres is for storing arbitrary text data. In contrast to a lot of other database systems, Postgres doesn't have limits on what the size of data you can put inside of there is. You don't have to say this is a varchar 10 or 25 or 1,000 or whatever. By default, you can just put any size in there, and if you want to have specific restrictions on size for what's going in, you would add like a check constraint on top of it, or use I think the varchar type does that implicitly if you say it's a particular size. In practice, if you're actually putting something that's ginormous in there, like you put like a gigabyte of text, it will work in the sense that it will support up to, I think, like a gig of text. If you do that, you're going to have all kinds of other problems anyway, because you have to actually have a gigabyte of memory to represent the object in your client. You have to get a gigabyte of memory on the database. Like, it's probably a bad idea. One other really nice thing about Postgres, which is one of those things that you don't notice it because, again, it just works, is the concept of like client and server encodings. The Postgres has a really clean separation of how the data is encoded and saved on disk for a given text column. And the client can actually say, I want the data in a completely different encoding. And it will do that translation for you. So you could have the data itself stored in one encoding, but say I want to get UTF-8 back or whatnot. In reality, I stick to using UTF-8 for everything across the board. And if someone's not using that, they should have a really good reason why they're not using UTF-8. But Postgres does support being able to do that, and it's a very clean separation, as opposed to coming from a lot of places where you're basically stuck with whatever the raw binary representation of that thing is, and you better hope it matches. I think I touched upon this in the beginning. There's the UUID type. A UUID is just 16 random bytes. It's literally just you go to /dev/urandom, give me 16 bytes, and that's going to be my UUID. In systems that don't have a UUID type, most people represent this as a string. There actually was a talk yesterday about converting a column from a UUID, which was a string, to an actual UUID type, in the interest of saving 36 minus 16 bytes per column, or technically 37 because they have a length in there too. It's really useful if you do any kind of like web development or whatever, where you just need IDs. You probably have UUIDs in there somewhere. And having an actual type for it's great because it represents what it's supposed to be. I go look at the field. It's not text. This is a UUID. Like I know what's going to be in there, and it'll validate to make sure it has that structure. JSON. JSON's a fantastic data type. It's basically like the catch-all type for I don't know what to do with my data, so I'm just going to put it in this random structure and go look at it some other time. It's been in there for a while. When it first came in, it wasn't that particularly useful because I think all you could do was just put it and get it back again. In 9.3, it actually became useful because now you have all these operators for I can dig into the JSON. So like if you look at this example over here, I'm saying, hey, give me the data field as a string from, give me the foo field of the JSON as a string. So that's what that double right bracket is. And then in 9.4, there's JSON-B, which is like a binary serialized form of JSON, which from an interaction point is basically the same thing. It just kind of stored in a much smarter, more efficient way, which lets you get into the nested structures better. I love JSON types, but it's one of those things where you can't just use them for everything, because it's not. If you just have like a bucket, like a 2-column table, like ID and data or something, you're kind of missing the point of why you have a relational database. But there are like legitimate use cases for JSON for being stored in the database, but also just for using it as a kind of transport mechanism. So some of the functions that were added for dealing with JSON, I think in 9.3, were row to JSON and JSON egg, both of which are like really useful for kind of combining together parent-child relationships. Because what row to JSON does is you give an arbitrary row in a table, and it'll give you a JSON object that represents the fields of that table with like name value for each thing inside of there. So in this case, I have let's see what this one's doing. Okay, so row to JSON does for one row, and JSON egg is the same concept as row to JSON, but it does it for putting it together into an array. So instead of just having one row represented as JSON, I can have an array of JSON. So in this case, what I'm actually doing is saying, hey, select from this parent table, and then as a subselect, so this is it's like a scalar subquery, but the value being returned back is going to be a JSON array, where I'm aggregating all the children to get a list of the children. So in like a normal parent-child relationship, if I want to get I have the parent, then I want to get the children, I'd have to do two separate queries. First, I do a query to get the parent, then I say select star from children or from child where parent ID is X. This is doing it in one pass, and I just bring it back as one object. And if your programming language you're using it actually supports, has native support for JSON, you immediately get this in a format that you want to use inside of your application. So to kind of see what this looks like, the results for this, like they're being pulled back with this JSON ag of the children. In one round trip, the first row has foo as the name, the type is Wizzle, and then I have an array with these three objects inside of it. And again, if my programming language naturally supports that kind of typing in there, I can just reference this as a child in there, and I don't have to do multiple round trips. So one other part of typing, which I don't think it's that popular, but I kind of like it because it's one of those things where you define something once and reuse it repeatedly, is domains. So domains let you define, it's almost like a subtype on an existing type, where you're restricting the values for that type to some subset. So like traditionally, that's something like I'll have a text column and I'll say that usernames have to start with a letter, be alphanumeric, or be maximum length or whatnot. And while you can do this in every single place that you're using something, so I could have like a username field in like 10 different tables and have that same check constraint there, by defining a domain on it, I only have to do that once. And then I can refer to it as a username type. And then just use that same username in like 10 different places. And if I ever need to go update something or like change the logic behind what defined the username, it's in one place. So if you want to make like kind of prefixed keys or things like that, you can define them with domains and then just use them. And from a driver perspective, interacting with this, generally speaking, you just get the data type for the underlying type. So if I define a domain for like account ID, like this account ID type, when I retrieve the value, I'm just going to get, like from the driver's perspective, it's just text. Like I'm getting back like a text value, but the database is enforcing it whenever I'm trying to convert to that type or insert into a field which has that type. So you can see over here, I've defined that person ID type once, the account ID type once, but I'm reusing them in multiple places. So I know my person table's ID field is a person ID. It's not just a regular text field. Same thing for on the account table, the owner of an account is a person. It's not just an arbitrary text field. And if you kind of go the route of having a prefix notation for your keys, this actually prevents being able to insert two different kinds of keys in the wrong place. Because like all my person fields, the person keys start with a P, the accounts start with an A. If you kind of use like a intelligent key system, which is kind of an interesting name for things like that, you can kind of prevent those kind of errors, as opposed to just having one generic, hey, random stuff goes inside of here. So partial indexes, this exists in a number of different database types. In Postgres, it's particularly nice because you can use them for very small specific subsets. So what partial indexes do is you define a subset of your table that you actually want to index. So in this case, I'm saying, I want to create an index on this menu table from the items on a menu, and I want to make sure it's unique for the isDaily special field. So what this does is it's saying I want to have it's a unique index, which means I can only have one value for this particular menu date. But I only want that to be true for when that isDaily special flag is set, which again is a Boolean. It represents what I actually want it to be. So what this does is it prevents me inserting two different things into the menu that are the special for that particular day. So you could have them for different days, just not for the same day. Partial indexes are also useful because they're just smaller. If you have some kind of like huge table, but some subset of that table is something that you can be looking up repeatedly, you can define a partial index on that subset if there's some way of defining what that is. And the maintenance of that index is going to be less too, and searching the index is going to be faster because it's smaller. So the other kind of fun or kind of better version of index in Postgres is what's called functional indexes. So instead of just indexing a column as it's represented in your database schema, you can actually index a function of that column. So in this case, I'm indexing the lower of name. So instead of just having name itself be indexed, I'm saying, hey, I want the lowercase version of name. And if you combine this with things like unique constraints, now you can say, hey, I want the lower of the name to always be unique. So one example of this might be if you have like usernames for a system, you might let people actually create uppercase usernames. Like for some reason you want to accept them to do that, but I don't want to be able to have like Alice with a capital A and Alice with a lowercase a because that's just going to get too confusing. So what you can do is have the field itself allow mixed case in there, but have a unique index on the lower. And Postgres will make sure that you do not insert two values inside of there, and it'll throw a constraint error if that comes up. And the way the functional indexes, they operate on it's a expression. It's not necessarily just like one function operating like lower or upper or something. It's really just any expression that you can put inside of there. And that includes using operators on things like JSON. So if I have like a JSON field, I can dereference the value inside it to say, hey, give me the name field of this data. And the double bracket here says I want it as the string value of whatever that is. And this is creating an index on that, like a regular B-tree index, which if I just use that same expression inside of my SQL, foo-data greater than name, it will use the index when I'm evaluating that query. So this is like, if you have, you generally shouldn't have lots of JSON in your data in your schemas anyway, because it's usually a sign that you don't really know what your schema is supposed to be doing. But if you do have some structure in there where there's something that you do want to index, and you have queries that are repeatedly hitting that same field, it's really easy to set that up because you just say, hey, how am I accessing this? Just literally copy and paste that inside of a index, and it'll show up. So on the a lot of this stuff I'm going through is more from like an app dev perspective of things that developers like to use when they're building applications to make life easier. And one part of that is doing schema migrations. So if you're coming from basically any other database, when you're doing schema migrations, it's all or nothing. You start doing something, I alter this table, I create this other table, I add an index, I drop a column, and hopefully everything works and we're done. But if it doesn't work, then you're in this like inconsistent state in between where like half of my migration completed, but the other half didn't, and you have to manually go fix it. Postgres has transactional DDL. Like this is one of the most pleasant features ever of doing schema migrations. You can add a table, create an index, insert data, modify something, delete something, run migrations. Like you do like 10,000 different things. And then at the end you can commit, or you can just roll back and it's as if nothing ever happened. So there's like some small limitations as far as some things that just aren't supported in transactional DDL. So like enums was one of those things where you could define them before, you could create new ones inside a transaction, but you couldn't add a new value. But in Postgres 11, actually, you can, I think. There's going to be a new thing with anonymous do blocks, which lets you do that. Outside of that, though, for like any normal schema migration, it just works because from the perspective of an app dev putting together something, I don't have to deal with that inconsistent state of, hey, half my migration applied, now I have to go back and figure out which ones it was specifically and skim through logs. It's all or nothing. Copy is just an awesome command by itself. It's literally the fastest way to get data out of the system. It's kind of low level as far as compared to getting actual fields back, because you're telling Postgres, hey, just literally send me data from this thing in some kind of serialized structure. But if you have that kind of requirement in your application, copy is really great for that, because the one other nice thing about it is since it's naturally streaming, if you stream the data out in the format that you want to use afterwards, you can just directly send it to the client. So like in this example, I'm formatting like some CSV data from some gigantic thing, and I could have the response from like a web request directly generate that data. So I gave a talk 2 days ago on Node.js, like a tutorial, and one of the examples we had in there was doing specifically this, where you could have this massive amount of data coming back and just directly connecting a pipe from your database through your web server to the client, so it just streams the whole file back, and you don't have to worry about being able to buffer a meg, 10 megs, a gigabyte, or whatever in memory. So kind of more tied to the schema migrations is, in my mind, because of how I use them, is to template databases. So Postgres has this concept of template databases, and what these actually are for is that when you create a database in Postgres, it's actually a copy of some existing database. So if you just say create database X, what it actually does is it creates a copy of template 1. And if you want to use a different template, like an existing database, you can specify that as a template instead. So my standard mechanism for doing any kind of schema migration for an application is the first step, I create a backup of the database by saying create database XYZ backup, usually with some kind of date suffix. And I use the current database, like the app itself, as the template. Now, this works. This isn't something you would do in production because you have to literally copy the entire database. But if you're working locally, like in a VM or something, where you have just the structure of the system, but not necessarily gigabytes of data or terabytes of data inside of there, it runs basically instantaneously. So once you've created that backup, now I can start doing stuff in this database. And I can actually drop my existing database and then create it again from that template as many times as I want. So like, let's say I'm testing, I'm literally testing out schema migrations. So while I can roll them back to see if they didn't work, I want to see them work because I want to build the schema, build the index, add a table, add a field, and then run my app code against it. But then I realized that this made no sense. I want to go back again. So then I just drop the applet, like drop the database on my local VM, and then create it again from a template and just continue again. And the whole process, if you're dealing with like a small database as far as something local, it takes like less than a second. So it's like a really great iterative cycle where if you compare this to working with literally any other database system, it's a real pain because then you have to, I have to export it out, like find some delete mechanism, use whatever their custom restore tool is for it. Whereas for Postgres, it's literally 2 commands. Just drop it and recreate it. And the only catch is that you can't be connected to the database. So that's like some intermediate stuff. Now, as far as like making hard things a little easier, so one classic problem in like computer science when you're dealing with constraints on data is if you have like a hotel, and you don't want multiple people to be in the same room at the same time. It's not that kind of hotel. So how do you kind of prevent that from happening using constraints? So if you're in like a, let's say, less expressive database where you don't have these full functionality at your disposal, there is some things that you could add on there. You could say, okay, I'm going to have 2 different fields for representing where I'm staying, like the booking period. So I have the start date and the end date. I probably want to have the end date be greater than the start date because it doesn't really make sense to go check out before you checked in. I probably don't want to have 2 people start on the same day because if someone's checking in, someone else isn't going to check in at the same time. But that doesn't solve the full problem in that if I'm staying for 5 days and someone else is coming the day afterward, they shouldn't be able to check into that same room. So if your database doesn't naturally support restricting that kind of thing in the database, your only real bet is to serialize the updates. And by that I mean whenever you're trying to do these kind of things, you'll do a select for update on the on the room, let's say, and then make sure no one else is touching this thing. See if whatever I'm trying to do is is acceptable. Is there anything else for that period in the next n days? And the main problem with that is it's error prone because you might do that in your application, but you have to do that in all your applications. That includes like any kind of like one-off script that's like cleaning some data up in the background. If someone else writes something, they have to include it in there. It ends up being like anytime you have to do the same thing in multiple places in programming, it leads to problem because there's always that one place where you forgot to do it. In Postgres, you can do this literally with one index. You just create an index called that excludes on that range. So what that means is you're saying, create this index, match on room ID equals. So if the room ID is the same, and then exclude on the intersection of the booking dates. So what this will do, if I try to insert 2 rows that violate that constraint, Postgres won't let me insert them. So I don't have to worry about like different parts of my application actually going through the same, having that same logic in there because it's handled by the database. And it actually also lets you it doesn't matter where it comes from. So kind of as an example of what this looks like, these numbers over here represent like the days of a month, like day 1, day 2, and these are like different rooms I have. So you'll see this first room I have from day 1 to day 9. I'm checking out on day 10. And this next room I'm checking in on day 10, checking out on day 18. And this third one over here, I'm trying to check in on day 5 and then check out on day 15. So you see the first 2 rows enter, but when the third row gets inserted in there, Postgres says, hey, you're violating the constraint on this, and we're not going to let you insert this row. And it's similar to validation for data types and just structure in general for like parent-child relationships. Having exclusion constraints is great because I can trust the data inside of my system. I don't have to worry about maintaining it in that particular state. Really cool stuff. So now we're going to get to the kind of more interesting things you can do with just Postgres. So let's say we have this like hypothetical example, which probably a lot of people have this kind of thing, where you have a primary database for your application, right? So you have the core data for your app, your customers, your accounts, your whatnot. And then let's say this is like a software as a service platform, but you also have like an on-premises platform for the same thing. So you kind of separate out the billing code from the core app code. So now we have a separate billing database. And separate from that, we also have like our core website where we're tracking we have Google Analytics piping in through Kafka or something, accumulating somewhere. And separate from that, we also are using Redis because we're using Redis for sessions, and Redis is awesome. So we want to find something that's going to kind of piece together all this stuff in one place where, I want to know, who's on the system, how much money are we making from this guy, how often have they been there, whatnot. Now, Postgres has this really cool feature called foreign data wrappers. Foreign data wrappers let you connect to something as if it's part of your database. So you can define a foreign data wrapper for a given database type. You define foreign tables representing some relation somewhere else in that other system. And then you can query them inside of your Postgres database as if it's a local table. So there's foreign data wrappers for all kinds of different systems. The core Postgres comes with, I think, 2. There's one for files and one for talking to Postgres itself. But there's also foreign data wrappers for talking to Redis, for talking to MySQL. There's, you can write foreign data wrappers that don't even talk to databases. Like you can just have one that makes up data because it's literally just running a program that's spitting back data in a particular format, like responding to the Postgres APIs. So you could have a foreign data wrapper talking to an API, for example. So using foreign data wrappers, I can define a foreign data wrapper for my separate billing database or whatever it is. So I say, create the extension for the Postgres FDW within my system. I define the billing DB, and you have a whole bunch of credentials and stuff in there for it. You define the user mapping to say how am I actually going to connect to this database, the username and password on the other side. And then finally, you define the actual foreign table. So over here on the table, on my local database, I'm saying it has an ID, a customer ID created at an amount. And in this case, it's a foreign table, though, and the server is that billing DB. So anytime I try to select from this, what Postgres will do, it will connect to that other database and just give me data back matching whatever I'm trying to do. But I get to do it from my system. And then similar for Redis, there's a Redis FDW extension that lets you talk to Redis as if it's a database. Now, the Redis one's a little different because it's not like a relational database, because Redis is a key value store. It has data structures for like lists and things like that. So the way that you use it is a little different than the Postgres FDW in that you can really just get a value or set a value dealing with Redis. But that's still like pretty good because you can do some really fun stuff. So now, kind of piecing all these things together, I can have a query that first goes to my core customer table, the billing table, pulls back the customers that have been billed in the past 30 days. So give me the transactions that were greater than now minus 30 days ago, using this really cool cast syntax for intervals, which is really nice. Then joining that to my local customer table. So this is the one inside my local system. And then I'm going to lateral that. So now I have my customer. I want to say go to Redis and pull out the key matching the session for that customer. So the way this would work is if I'm doing in my app, I have it set up so that when a customer session gets created, the structure of that key inside in Redis is going to match this particular format. So that's how I know what to look for. But what this ends up doing is this last piece over here represents that customer session. And in this case, it would be only if they're there. If I wanted to, I could actually have this outer join to that as well to get the session if it's there and get nothing otherwise. And then the stuff that's inside of in Redis, assuming you're using Redis from something like you're putting more than one thing inside of there for the session. Let's say it's some JSON inside of Redis. I can use the standard JSON operators inside of Postgres to pull out those values and convert them into actual types in Postgres. So now I have all my customer details. I have the total amount I've billed them for the past 30 days, and I can actually see, hey, is this guy online? When's the last time he was there? All in one query. So this kind of thing, you can do it by building an application that talks to all these things. But if I want to change like one piece of that, then I have to go back and change the whole application basically because how it's working. FDWs are really, really powerful. I saw I think last year or the year before, I saw a talk where the idea was using FDWs almost as a data warehouse focal point. Oh, that was you guys, yeah. It was a really cool idea. It was basically saying, hey, I have this empty database. I'm just going to put like 1,000 FDWs inside of there connecting to everything. And we'll just use Postgres to link everything together. Having like different FDWs is also fun too because you can pull in all the different types of things that you have because you don't just use one data store. Personally, I love using Redis for sessions and like ephemeral state, and I love using Postgres for persistence. So kind of like looping back again. The whole point of this isn't like, it's not really like ANSI versus non-ANSI. It's really just embracing whatever platform you're using. In my particular case, I love using Postgres because there's so many features there. And instead of just trying to go to that lowest common denominator of, hey, what is the one select where ID equals X or whatever I can use on every single system, you embrace the system itself because there's so much stuff over there that just makes your life easier. And then you end up being able to do things that just wouldn't be possible otherwise in your apps. So that's kind of my presentation. Any questions?
I can have some comments.
Sure.
Basically, first of all, that's actually quite awesome. So we use most of all these features. Couple of things I wanted to highlight. So domain, actually, that's interesting because domain is not ANSI SQL, but it is actually relational concept.
Mm-hmm.
When SQL became standard, they threw away some of relational concepts. So basically, the reason why domain is in Postgres is because Postgres was designed by Mike Stonebreaker, and he wanted to do actual relational model. One of the uses actually which we utilize for domains, for our bitemporal model, which was our other talk, last year. So we define all bitemporal framework because you use these intervals for dates. Some people use it for timestamps, some for timestamps with or without time zones. So what we do, we define all bitemporal framework on domain, which is called time period, and then each time we install it, we define what is this domain. So then all low-level functions can run whatever domain this particular installation wants. So that is super cool. One more comment, because again, I know you know, but you didn't mention it. I myself actually stumbled on it when I was first using the partial indices. When you query and want to use these indices, this particular condition should be written in your query.
Oh, yeah.
Exactly as yes, but I mean that's not. One of
No, because otherwise it won't use the partial index because it has to be the piece. Yeah.
One of the first indices I built, I was super proud. We had email for customer and alternative email, which was now in 90% of cases. So I actually built partial index, on alternative email where alternative is not null, right? And then I was running the same query I did, why in the world is not using?
Because it doesn't have the where clause in the, yeah.
Why does it know? Because I asked alternative email is something. Cannot this thing figure out that if it's something, then it's not null? So apparently it does not. So that was one of these.
Yeah, it's important whenever you're using them that you have to always include the where clause in there. Yeah. And generally speaking, you do it when you have that's the subset you're going to be looking at anyway. So it's the index clause itself matches one-to-one to what you're trying to tell your query.
That's important. So then you actually use all this cool stuff with partial indices, all this functional. So this can be actually, pretty pointed. And we do use it just with exclusion. Actually, this such a cool thing. I couldn't believe when I discovered.
It's like magic.
Oh my God, no, that's a lifesaver actually for everything. And we use for data repository, basically combining everything in one place. So that's I think actually all the things you mentioned, they're super cool Postgres features.
Good. You have a question?
So in there you showed your transactional DDL, and then the next slide or two you showed doing the migrations because you did a backup. Yeah, this. So can you create a template from a backup and then do a bunch of changes to it and then create another template and then do a diff to get the screen before?
There's nothing native. So the question is, if you create a template and then create another, do you make changes to it? Can you kind of make a diff of what it is? There's nothing built in that does that. There is some external stuff, just open source stuff people have put together to do a diff between two different databases. I personally don't do that because I've never found the need to do that, because whenever I'm doing any kind of migration, usually it's of the form, here's my base state, and then I'm putting together an actual script of do A, do B, do C, do D. And if it doesn't work, I just go back to the base, edit the script, and run it again. It's that's the cycle of edit the script, run the thing, go back again till it gets to the point that you want it to be.
So you just take notes. I did it.
Yeah,
I added a table. I added a column.
But you can create. If you create a database off a template, you can create another database off that one afterwards. as many as you want. It's not, there's no limit to it. And again, the only real catch is like doing this in production. While in theory it works, but it literally requires copying the entire data directory. So anything that's non-trivial is gonna, it's gonna take some time. But for like dev and like a VM or something, it's like that. Any question?
Yeah, you were talking about lateral. I'm not familiar with lateral, but it caught my eye because it's in the from clause.
Let me see where.
We did a wall recently on the way common table expressions are fully materialized. Do you know if you can, is lateral, being part of a join, is that?
It gets optimized. I might not be the best person to answer this, but it's not like common table expressions where there's no barrier there as far as being fully materialized. Generally speaking, I think it does get evaluated as like a nested loop because conceptually that's what you're doing. You're starting off with from driving data and then saying, hey, give me the rest of the thing for each one. And usually where you use it is in that kind of situation where I have some set, like in this case where I have a customer, and I want to pull out the most recent purchase for that person. So it is like implicitly is a nested loop kind of concept where I'm saying for each guy, give me this one thing. And it is something that you can do. Like you don't necessarily need lateral. It just makes it so much more pleasant because it replaces like a series of scalar subqueries with one relational representation of what that is.
One on each of the
Yeah.
subqueries.
If you're coming from another database and like trying to put together some kind of weird reporting query or something, you've probably seen stuff where it's literally the same query 10 times in a row with the only thing changing is like the field for, I want field A, field B, field C, field D, and all these different scalar subqueries. When in reality, you're saying, hey, give me that record and then do something with it.
We got this problem where we're trying to do a fine-grained permission model over our data for our customers. And we got this monster of a query that sort of like expands out to join a bunch of our stuff that are related by a star of relations and then applies fine-grained permissions per user to see what a user can see.
Mm-hmm.
And we like to have a reusable way of then using that to generate reports.
So that's actually a really fun.
And we ran into that wall with CTEs that like,
CTEs are not good for this.
they're not good for this. And we're looking for what the right idiom would be that would be elegant for that.
See, the CTE is an optimization barrier, so it doesn't work over there. But there's also other issues with that. In that you should look at security barriers because even though you can't see something, doesn't mean that you can't interact with it. So if you have like I'm just kind of getting sidetracked, but you can query like a table and say like basically throw an exception if I'm able to read like if it matches some state, because that filter like the optimizer gets to pick what order it's running things. So you could actually kind of like leak information out unless you explicitly go out of your way to have a security barrier to prevent data coming out of a view, which Postgres supports doing those things, but you have to be explicit about it. Because in the normal case, the optimizer wants to have as much information as possible to do the optimization. Question?
I just wanted to say, there's a commit fest item, like a proposal for Postgres 12 that makes CTEs not
materialized. Yeah.
You should go test that and say say that it's important and you want it. Thank you.
Taking the lateral example that you have here, we do something very similar, but get rid of the lateral and take the entire select and throw it above the from. And we'll either JSON ag if we want multiple fields or aggregate. And so that entire subject, but is that the same thing as just the lateral, just in a different place of the word lateral? Or?
It is the same. So the question is, or the comment saying that instead of having the lateral, you can actually push the same query up there and use something like JSON ag or row to JSON. Yeah, if it's an aggregate. The use case for this is having the typing for what you're doing and like being able to reference it, as opposed to converting it to something like JSON. Although I have that example in here somewhere too with the I don't know where the JSON. I think JSON types were afterwards. Of doing that same kind of thing when you want to bring it back, because the JSON one gets more interesting when it's not even just one flat structure, but you want to bring back like an array of values, like a parent-child relationship. Because instead of just getting one, now I can say, hey, give me all the children or whatever, which isn't necessarily directly representable with like a lateral, because like lateral, I'm still getting one row. I'm transposing it and turning like the join into one thing. Whereas like this, I'm saying get all of them.
But you got that one because you said limit one.
Yeah, but even if I didn't, I'd end up with multiple rows. I wouldn't have one row per person as opposed to being in the scalar portion at the top. So like using them together is like a common thing too. Any other questions? All right, thank you.